Welcome viewers. After India has made history with the Chandrayaan-3 moon launch, it has now set its eyes on the sun. These scientific breakthroughs back to back are like feathers on our country's hat. In fact, these celestial bodies are very important and are considered as sacred bodies in multiple global religions. The sun is the central body of our solar system. The world revolves around it, and it is a source of energy for all planets, including the Earth. Today, I am joined by all the scientists who have played behind the scenes to make this project a grand success. And I am Srinidhi, reaching out to you from the Satish Dhawan Space Center, Sriharikota. And today we'll be discussing about the impact and the benefits of the Aditya L1 space mission. So today we are joined by Dr. Anil Bharadwaj, Director of PRL, Professor Annapurni Subramanian, Director of Indian Institute of Astrophysics, Dr. Sankara Subramanian, Principal Scientist of Aditya L1 mission, Dr. Durgesh Tripathi, PI of SCYT, Dr. Dipankar Banerjee, Director of IRIS, Nainital, Dr. Satish Tampi, PI of PAPA, and Dr. Vipin K. Yadav, PI of Magnetometer, joining us today for a 25-minute fireside chat on the sidelines of Aditya L1 launch. To start with the Principal Scientist and PI of SOLEX, Dr. Sankara Subramaniam, why is Aditya L1 mission so important and what are the objectives of this mission?
Thanks a lot. First of all, let me thank ISRO as well as the Government of India for providing a great opportunity for the solar and heliophysics community of the country. Both solar, heliophysics as well as astronomy thrives on data. More the data you have, we get more understanding about the system. And sun is our own star, our dearmost star, so understanding them is much more important for our everyday life. So this mission, Aditya, when it was conceived initially, with a support from our Professor U.R. Rao, along with Dr. Srikumar and Professor G. Srinivasan, we made sure that we will have a unique data set which is not available from any other missions internationally. So the 7 payloads what was conceived for this particular mission will provide a unique set of data which is currently not available from any other missions, which will provide us new insight into the solar and heliophysics community in India and provides some important aspects like the initiation of the coronal mass ejections, the speed at which it gets initiated, and some wavebands which are very important for the Earth ionospheric connections like near ultraviolet band, and the high energy particles, which is high energy radiations as well as particles which is coming from the solar flares and coronal mass ejections. So these are the informations which would be available from this particular mission, which will allow us to understand the sun, its dynamics, as well as the inner heliosphere, which is an important element for the current day technology as well as the space weather aspects of it.
Thank you so much for your remarks, sir. So now we'll move on to Dr. Anil Bharadwaj. So the sun is a very important energy source of life. Having understood that, it creates a trouble when it's angry. How does Aditya L1 helps us through the mission?
Thank you and good morning, viewers. First of all, let me tell you that Aditya L1 is a multi-wavelength, multi-instrument and multi-directional mission. Multi-wavelength because it works in X-rays, UV and visible. Multi-instrument because there are 7 experiments on board. And multi-directional because it looks not only in the sun direction but also around it. Now when the sun becomes angry, there are 2 types of process which happens. One is solar flares, that means electromagnetic radiation, which reaches the Earth in 8 minutes. But along with that, there is a mass which is also ejected out in form of plasma, and that can take about 2 to 4 days to reach the Earth. What we are looking for from the Aditya L1 mission is to see the impact of solar flares as well as coronal mass ejections as they come to the Earth. We have instruments which look at not only in the sun direction, but also in other directions, for example, perpendicular to ecliptic or in the earth directions. The impact is that we need to see when the sun becomes quite angry, what are the ways in which it is affecting the planet Earth, and L1 point being at point L1, which is just 1% away from the Earth, it is able to provide us a lot of new informations of the plasma and the electromagnetic radiations which is reaching the planet Earth.
Thank you so much, sir. So now we'll move on to Dr. Annapurni Subramaniam. So the science behind this mission is very unique. So what's the impact of this on the Earth and also on the heliosphere?
Yeah, so thank you for having me on this show. To put the thing in context, I'm the director of Indian Institute of Astrophysics, and we have delivered one of the major payloads on this mission. This is the visible emission line coronagraph. So if you actually look at the words used in it, it is visible because it is seeing the sun and the visible wavelength. Emission line, so what is it detecting? It is the emission line of certain elements. Because the corona is hot, the emission which you get is in the terms of, it's not absorbing the light which is coming from the sun, but it's already hot, so it is coming down by emitting lines. So we are tracking these lines using what? A coronagraph. Now what is a coronagraph? This instrument makes a total solar eclipse all the time within the instrument. So you are looking at the sun all the time, 24/7, through using this mission, and this instrument looks at the sun as though it is always in total solar eclipse. Now, why you want to have the eclipse all the time? Because you want to see the corona. Why corona? Because when sun burps, when sun is angry, the corona is what it takes the matter away. Now, what is unique about this instrument? This is going to see the corona as close as possible from the disk of the sun. Now, what is so challenging about it? It is because the sun's corona is 1,000,000 times fainter than the disk of the sun. So you have to not see the disk of the sun, but see only the corona. So this instrument is very difficult to make, challenging, but it is made. Now it's going to the orbit. Now what we plan to study using this instrument is the corona, its dynamics. Through this emission line, you can actually measure the velocity by simple physics called Doppler effect. So you can measure the velocity, you can measure how much matter is moving, and eventually how that matter will come to the Earth and the heliosphere. So it's overall this instrument, along with the others, of course, the other PI will also be explaining about it. So these holistically will give you a lot of information regarding not only the sun, but also the heliosphere. Thank you.
That was very interesting, Doctor. Thank you very much. And now we'll move on to Durgesh Tripathi, Dr. Durgesh Tripathi. You are the PI of the for the payload suit. How is that different from other telescopes like Hubble or James Webb? And what are you going to investigate using this?
Yeah, so good afternoon. My voice is going to mumble because I'm still in the awe of the launch, and one of the payload is gone there. So essentially, JWST, which is James Webb Telescope, and the Hubble Telescope, they are going to look at the universe, different objects, galaxies, star formation, and other objects you see in the universe. Whereas when we talk about Aditya L1, it is going to look at one particular object, which is our sun. And it's also kept on the other side of the sun-Earth line at the L1 point, whereas the James Webb Telescope went on the other side of the Earth, which is at the L2 point. Now, the scientific difference, of course, they also observe in ultraviolet, but Aditya, as Professor Anil Bharadwaj and also Professor Annapurni Subramaniam alluded to, these are multi-wavelength satellite, and they will be observing all across the electromagnetic spectrum. In particular, suit is going to be looking at the ultraviolet radiation in 2000 to 4000 angstrom, if that matters to you, emits from the lower and the middle atmosphere of the sun. And what we want to look at that how in general the sun's atmosphere is coupled by looking at the observations at various height, and how actually this radiation is coming and getting absorbed in the Earth's atmosphere, and what kind of effect it can have in the chemistry of ozone and oxygen, for example, and also these explosions which are happening, how much radiation they are creating, and how much effect it might have. Thank you.